Recording. So today, after a while, I had a trip. We're gonna continue on the algebra stuff, and today is chapter 11, right? And we're gonna talk about cyclic groups, which starts my series of questions, I guess. If G is a group and A is contained in G, it may happen that every element of G is a part of A. And then, can somebody refresh my memory? Does it mean being a power of A in this context the same as applying the function, the the function of the group these many times, or am I tripping?
Uh, well, it is applying the function, but it's actually that many times plus one because you're counting the number of A's, not the number of applications.
Sure thing, but this being a power of A means applying F that many times.
Uh,
It means combining A that many times, I guess.
Okay,
yeah.
so
A
it's
better way.
not what I said then. It is just gluing them together.
Well, it's A
Going by
times
the
A times A
function,
times A. There are n A's. There are n minus one applications of the function.
Um, yeah. Well, I guess that distinction is important, but I'm fine with that. In other words, G may consist of all the powers of A and nothing else. And that's what we're gonna say. In that case, G is called a cyclic group, and A is called its generator. We've seen this concept before, but I keep getting myself confused if the generator, the seed of the whole process being called a generator means that we are generating the other members of the group by applying A with itself with the binary operation, or if it's just a gluing process. I keep getting myself confused.
Basically, you pick an element, and then using only the element and its inverse, you derive all the other elements of the group, and that's a
But
cyclic group.
and the F, the element, its inverse, and F, right?
And the function of the group, yes, you do need that.
Okay, so it's not just a gluing process. You are in fact um, applying F many times.
you can't have a group without an operator, so yes.
Yeah. Okay, that's fine. If I don't remember, there was a terminology for this angle brackets thing, but if this is true, is a cyclic group generated by A, and A has order n, we say that G is a cyclic group of order n. We'll see in a moment. In that case, G has exactly any elements. If the generator of G has order infinity, then we say that the order is infinity, and it has infinitely many elements. Cool. The simplest example is integers, which consists of all the multiples of 1. Okay, can somebody help me here? Um, which function is the multiples of 1 is using here?
Addition.
Okay. Okay, so this is doing 1 plus 1 and grabbing the answer of that and doing another plus 1 and so on and so forth.
Yeah, and that gives you all the integers.
Yeah. Integer is a cyclic group of order infinity. Its generator is 1. Another example of the cyclic group is the modulo 6 stuff, which we've seen before, which consists of all the multiples of 1 added modulo 6. Um, um, but the modulo 6 has another generator. What is it? I think we've seen this before, right? I don't remember, but I do remember. I don't remember the answer to that, but I do remember we've seen that before.
Well, because the generator comes with its inverse, 1 works, but also minus 1 works, and minus 1 modulo 6 is equal to 5, so that's the other generator.
Makes sense. Because we need to have an odd number eventually to do the whole thing, right? Cool. Suppose that this is a cyclic group whose generator A has order n. Since that is a set of all the powers of A, it follows from the theorem, blah blah blah. So yeah, we've seen this before also. If you compare this group with integers n, we notice a remarkable resemblance. Yeah, so then now we're going to essentially do the isomorphism, which, well, in this case, I do remember that from the previous reading. We just have to do the one way, but in this case, you can actually do both. So the arrows are like bidirectional, uh, and then so then you can map it, and this is a very important property to check if it holds. And then f is an isomorphism from integers n to. How are we gonna call this? Um, cyclic A? What's the name you guys are giving to this thing?
That's a decent name, I guess.
Okay, cyclic A. In conclusion, they are isomorphic, and there we go. Let us review the situation in the case where A has order infinity, blah, and then this is the isomorphic to integers instead of bounded integers, let's say. Um, yeah, and this is cool. Like, this theorem is very cool, partially because of the fact that it is very intuitive, at least to me. For every positive integer n, every cyclic group of order n is isomorphic to integers bounded to n. Thus, any two cyclic groups of order n are isomorphic to each other. And why? Because you can always put them, we can always put any two groups in common grounds because you can always exploit the isomorphism to integers. So there is like an automatic bridge between any two cyclic groups of order n, of course. And then it goes, every cyclic group of order infinity is isomorphic to integers, and therefore any two cyclic groups of order infinity are isomorphic to each other for the same argument, right? And I think this is very cool because it makes so much sense, right? If you have two things and they can go to something that is the same, then you can go from one to the other, right? That's cool. And then of course we have to, intuition is not enough, so we have to state more stuff. If G is any group and A is containing G, it is easy to see that the product of any two powers of A is a power of A, of course. Furthermore, the inverse of any power of A is a power of A, again, of course, is a power of A. It therefore follows that the set of all the powers of A is a subgroup of G. This subgroup is called the cyclic subgroup of G generated by A. It is obviously a cyclic group and therefore we denote it by cycle of A. If the element A has order n, then, as we have seen, cyclic A contains the n elements, those. If A has order infinity, then those. And for example, in integers, cyclic of 2 is a cyclic group of integers which consists of all the multiples of 2. And in Z15, integers bound by 15, 3 is a cyclic subgroup of all those that are multiple of 3's, but the ceiling is 15, right? Which contains all the multiples of 3. Actually, this is modulo 15, right? I was reading this wrong. Because when there is the subscript here is modulo. So that's why 15 is not appearing here. And then in S3, then there's that. Same principle. Can a cyclic group, such as integers, have a subgroup which is not a cyclic? That's a very interesting question. The question is of great importance in our understanding of cyclic groups, and it's not obvious. Although this pisses me off because there is like the answer is not obvious, but the plot is obvious for whatever reason, and I hate when they do that because they try to be humble in the beginning, but then they say fuck you later. Why? That's so annoying. Okay. So what are we trying to prove with this theorem? Every subgroup of a cyclic group is cyclic. We are trying to prove that if we have a subgroup of a group and we know the group is cyclic, if the subgroup can also be cyclic in the definition we've seen above, which means you can generate all the elements given a generator. Cool. So let's see. And then this beginning is very fine, but I have a question about this obviously here. So let's say that G is equal to cyclic of A, which is a cyclic group, and let H be any subgroup of G. We wish to prove that H is cyclic. Every H, possible H, is cyclic, actually. Now, G has a generator A, and when we say that H is cyclic, what we mean is that H2 has a generator, which we're going to call it B, and H consists of all the powers of B. The gist of this proof, therefore, is to find a generator of H and then check that every element of H is a power of this generator. And this is very fine so far, right? This is exactly what I was thinking of. And it continues. Here's the idea. G is the cyclic group generated by A, and H is a subgroup of G. Every element of H is therefore in G, which means that every element of H is some power of A, which is also true. The generator of H, which we are searching for, is therefore one of the powers of A. One of the powers of A, which happens to be in H. But which one? Obviously the lowest one. Okay, can somebody help me here? What happened in this jump here? How can we went from hypothesizing to obviously the lowest one? I missed something. So can somebody help me with that?
Well, if you only have the group operation and the elements in H, and you want to find one element that you can combine to make the others, well, if you pick one that's not the lowest one, you run the risk of not being able to generate every one of them.
Oh, okay, so you're looking for the lowest ones because those are the seeds. That's why.
Yeah, because like if you have a higher power and you can get it from a lower power, then why not just start with the lower power to begin with? And then if you follow that argument to the end, you end up with the lowest one.
That should be written here instead of this obviously here. But okay, it makes sense. We are looking for the lowest because that's a safer bet that you're going to be able to generate stuff because they are lower, right? If you have a higher one, you cannot guarantee you have a lower chance of generating the rest of them. Okay, cool. So, and now carefully, here's the proof. So let m be the smallest positive integer such that this is true. We will show that every element of H is a power of am, hence am is a generator of H. Then we're going to use a division algorithm, and we're going to use the same thing as we always do, which is to try to make this equals to 0, like r equals to 0. And we're going to say that by saying that, hey, manipulating the expression, blah, 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 like multiple times, doesn't really matter. Okay, so that actually explain what happened in here. So we have this on the one side, and we have this in the other side. We are passing the a to the power of mq to the other side, but we don't want to, like, we want to keep all multiplication, so this goes to the power of -1, which is equal to the a to the power of r on the other side. Then you can manipulate the thing, and then you have this thing on one side and this thing on the other side. But we know that by hypothesis that am is contained in H, and that AT is contained in H. I don't remember why is a to the power of t in H. I've seen this before in another. We've seen this before in other proofs, but I don't remember the argument because again, 2 weeks since this thing.
Well, it's because we're picking an arbitrary element of H to be a to the t. So it is in H by our hypothesis.
Oh, okay. Okay, so this is inside. This is in. Wait, this is in. And this is in. So this is in as well. It follows that a to the power of r. Wait a moment though. If we know that these two things are true, how can we know that this is also the case? How is Q participating in the party here in this case?
Well, we know because we know the one inside of the parentheses is a member of H, right?
Yes.
And Q is an arbitrary integer, which we don't know what it is, but it's an integer, which means it's a
power
power.
of h to the m. Yes, I see.
Yeah.
Yes, it follows that this is true, but we know by the division algorithm that r needs to be smaller than m, and m is the smallest possible integer. Well, there's a typo here. such that this is true, which means that R must be 0 and therefore T must be equal to that. Again, we've seen these proofs before with the whole division algorithm. That's fine. We conclude that every element h to the power of t is contained in H and is of this form, that is, a power of a to the m. Thus, H is a cyclic group generated by AM, which is also cool. And then we're gonna find, like, the final note of this chapter is also kind of, it's surprising and a little bit kind of confusing to me, because in my mind this should be n minus 1, but maybe I'm wrong. I'm probably wrong. So let G be a group, as we have seen. The order of an element in G is the least positive integer n, such that if you apply the function n amount of times using a, you're gonna get to the identity element. Earlier we defined the order of the group G to be the number of elements in G, which is a much simpler thing, right? And then remember that we denote that by the pipes. These are two separate things, but apparently there is a connection between them, which is, again, my final question, aside from the exercises. Let A be an element of order n in a group, right? So it's the order of the element, right? So that means that if you apply A in, if there are n factors of n, you're gonna get identity, right? By this, there are exactly n different powers of A, hence cyclic of A has any elements. Yeah, of course. The thing that's generating the order is a cycle, right? Because by the definition, we're only using A's to generate the stuff. So it's like, this is assuming you understood that. Thus, the order of the element n, then the amount, the number of elements in the cyclic of A is also n. That is, the order of a cyclic group is the same as the order of its generator. So here's the thing. Here's my question. That's the hard part, remembering my question. So we know that if you apply A n minus, no, n times. If you apply A n times, you're going to get identity element. But we want to know how many elements the cycle of A generates, right? So here's my question. If we get to n, we automatically go to identity, which we already had. And oh, maybe that's why it's n instead of n minus 1, because we're going to generate identity out of that. Is that the reason?
That's the reason, yeah.
Okay, got it. Cool. See, I am stupid, even after the trip, but not that stupid. I can still get there. Okay, and then about the exercises, I'm not gonna lie, I didn't have much time to focus on the exercises, so I'm completely like, you guys are driving this part. We have 40 minutes for it, so you guys are gonna tell me which exercises are. I read them, but I didn't think much of them, given how much time I had to read. Uh, so exercises A. Does anybody want to say something about it?
Uh, Not really. This is mostly straightforward, although it is interesting to note that rational numbers and real numbers, if you believe in them, are not cyclic if you actually work through the A7 exercise.
Okay, so that without the zero being cyclic. That without the zero being cyclic.
Well, in this case, it's the multiplicative group, right? But the point is, you can't really pick a unit because you can always make a smaller unit in that setting.
What about rationals though? You said rationals as well, right?
Well, yeah, you have the same you have the same problem because, like, okay, say you pick, well, you can't pick one because that's the unit. So let's say you pick, I don't know, a
Half?
half. Well,
Sure.
if you just use products of a half, powers of a half, first of all, you can't get anything. Actually, you can get things that are bigger than one, but you can't get any multiples of a third, for instance.
Hmm. Yeah, I guess that applies for both sets of numbers. Well, is that the answer? Do you know the answer to this one? There's no solution, but I think the answer is going to be no then.
Yeah, because like no matter what unit you pick, you always have a smaller element that you cannot generate from just powers of the unit. Um, so you're kind of stuck trying to make a cyclic group that's equal to, well, the multiplicative rationals or reals, I guess.
Sure, I follow that. I follow that. Okay, exercise B, I have a question. So there is a proof, it is asking us to prove that every cyclic group is abelian. So is my understanding that, well, I haven't proved, it, but my intuition is that because it's a bunch of things that are generated by the same generator, isn't that like already abelian by just like default?
Well, because every element can factor into the same element,
Yeah.
commutativity just becomes associativity, actually. It reduces to associativity, which is given by the fact that this is a group.
Yeah, but
And they
well,
are isomorphic to addition on the integers, so which is abelian.
oh yeah, that's also a very interesting point. I haven't thought of that. I just thought everything is the same. Swapping them out, what are we doing? But yeah, Tevo's argument is also an interesting one. I haven't thought of that. Okay, that's cool.
Well,
If
another way to think about it is they wouldn't be able to be isomorphic to the integers if they were not abelian, because then they would lack a property that the additive group on integers has.
Well, but that's a stronger statement because the isomorphism didn't utilize any of that to 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 do the stuff to make the argument. Like none of this said this. We are exploiting the fact that they are both abelian. Um, but well, I don't know. I prefer the category theory for program as a isomorphism definition than this one. So that's that's how I see it anyway. Like yes, I agree with Marinho that if they were not abelian, they couldn't be able to do the mapping. But this book doesn't use those type of things. It just uses the recipe thing, which is this is a step of the recipe, and well, it is what it is. Cool. Okay. So any other comments about B?
Um, well, not really just B, but pretty much all the exercises after this. A lot of these actually uses number theory because, like, of the isomorphism with integers. So number theory becomes very relevant here.
Yeah, no. There's even a hint somewhere saying, "Hey, I'm not expecting you to figure this one out without the knowledge of this. So I'm gonna give it to you." So that's cool. And there's a lot of relationships again about like being on not primes, which I find it a little bit overwhelming because this is an algebra book that there's nowhere written here that we should have a companion for number theory book. So it's kind of like juggling too many balls in my opinion. Uh, okay, so generators of cyclic groups. Anything worthwhile in C in you guys' opinions? I don't have that many opinions today because, like I said, I haven't spent that much time reading the exercises thoroughly as I should have. But I didn't have that much time this week. So that's my defense. Uh,
Well, if Tevo doesn't have a comment about C, I have one actually.
yes.
When I was thinking about well, this whole series of exercise C, I guess, but I didn't realize at first that there would be more than two generators for a finite cyclic group, but there can be actually.
Which exercise made you realize that?
Uh, it was specifically, mm, was it C2? Yeah, it was C2 actually. Um, when I was trying to figure out like C2, C3, I think, yeah, C2 and C3 basically. When I figured that
Mm,
out, in the course of figuring that out, I came to the conclusion that yeah, actually anything that's relatively prime to the thing is going to be a generator. And then I read through the exercise, and I reached 8, and I was like, oh yeah, actually I jumped to the end. That was what it was building up to, but well, I found that kind of funny actually. But yeah, it turns out if you have a finite cyclic group, um, any power that's relatively prime to the size of the group will be a generator because, well,
because?
number theory basically. But
Now, what is the intuition behind that? Don't give me like number theory, I guess.
well, it has to do with the properties of modular arithmetic. Specifically, uh, if you keep adding the same number repeatedly, right, and you're doing modular arithmetic, whether or not the 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 cycle that you build from that syncs up with the cycle of the whole group and therefore may end up eating some elements or not depends on whether they share any prime factors. Like for instance, if you try to repeatedly add 2 but your group has an even number of elements, we saw this before, right, where you end up landing on only half of the elements, right?
Yes, yes, I remember that.
But if you pick an even, or rather an odd number as your starting point, and you have an even number of elements, you end up going through all of them. And that's because even numbers, well, actually, if we pick a small number, right? If you pick a larger number, that may not be the case, but that's because, like, if you do like something like 8 elements and you do steps of 3, well, 3 is not a factor of 8, so the two cycles they never sync up, which means you end up going through the entire original cycle eventually.
Wait, but which ones are not syncing up? 3 and 8?
Yeah, because 3 is not a factor of 8, right? So if you do 3 plus 3, that's 6. Then you go to 9, which wraps back to 1, right?
Yes.
Then you go through 4 and 7 and 10, which wraps back to 2, right?
Yes.
And then you go through 5, and then you go to 8, which is 0, and then you're back to 3. Like, it only syncs up when you actually go through the whole cycle. So in some sense, actually, this has some connections to acoustics, oddly enough, um, because in some sense, if the element you pick um, has common prime factors with the total number of elements, it's kind of like you have a harmonic uh, of that of the whole
Wow.
group. Like I just thought of that actually. That's
Uh, I guess, right? I'm not into acoustics. I'm very simple tone in terms of instruments. But my understanding is that a harmonic is kind of like things that are related to each other in a way. Is that the relationship between them?
yeah, like basically
Crazy.
the harmonics of a wave are all of the waves where
I know that
if
one. I do.
you
I do know.
yeah, it's the same thing, right? All of the waves that have a length which equally divides the bigger wave, right? So like the first harmonic, you can fit two of the smaller wave inside of the bigger one. The third one, you can fit three, and so on.
Hmm. Can somebody remind me again the definition of relatively prime?
They don't share factors in common.
Oh, okay. That
Yeah,
is
specifically prime factors, right?
okay.
Well, I guess they wouldn't share any factors if they don't share any prime factors. So
Okay, but they don't share any common prime factors. That's what you guys are saying. Cool.
yeah.
Man, is it fair
Uh,
to say that? Okay, go Tiv.
oh no, I was just going to comment that you can get a glance from what Marinho was saying from the last exercise of B, but it's clearer here.
Last exercise of B.
It just kind of leads to what
Ah,
C is
okay.
talking about.
Again, automorphism is the thing mapped to itself.
It's an
Yeah, it's
isomorphism within itself, yes.
Okay. Yeah, no, modulo is very powerful, isn't it? Because at the end of the day, that is the operation. Well, that is the mental model that I have for things that are sync up. And if they don't sync up, the module is gonna fail somehow. So that's interesting.
well, modulo is the primitive for like cyclic behavior in general, right?
Well, yes, but it allows you to. Well, in a way, it is connected to the prime stuff, and when you have access to the prime stuff, it bridges number theory like automatically, doesn't it? So it's kind of
Uh,
like like something that you don't give that much points to it, but as you read more stuff, you're like, man, I'm relying on the fact that modulo can go get me to so many other places. So that's unexpectedly cool, I would say.
well, this is part of the reason why I don't complain about indexing in Python, actually. I complain about the scope, but not about the indexing. Because negative indexing is just, okay, you take the length of the list, you take your negative number, you do a modulo, and you get an index into the list. Like, it makes sense numerically.
No, I used a bunch of that in my college days in Python, like a lot. Um, but I never thought of that in this way. Anyway, D, elementary properties of cyclic subgroups of groups. So does anybody want to comment on any of these? And also remind me what the heck is a kth root that I forgot.
It's a B such that B to the power of K is A, or B n
No.
K times is A.
No, okay, so it's essentially what is the power that another number can be the power of that which is equal to A. Cool.
Yes.
Any comments so far on D?
Uh, Not really. Yeah, I have some comments on E actually, but not on D.
Let's go on E then. So what are your comments on E?
Well, um, point three, exercise three here in E is pretty interesting actually.
Okay, so we need to read two. So you have the Cartesian product GH as a cyclic group, then G and H are both cyclic. But 3 is saying that the opposite doesn't hold, which means that if you have G and H being both cyclic, not necessarily the product will be. What the example did you find of that?
Okay, this actually goes back to the whole harmonics thing in
Sure.
a weird way. Suppose you have, let's use just finite integers as the example because everything is isomorphic to those, right? Modular arithmetic. So if you say that okay, G is Z2 and age is Z3, then
Yes.
actually the product of those is cyclic. But it is cyclic because 2 and 3 are relatively prime to each other. If you pick 2 and 4 instead of 2 and 3, then you see that, okay, if you try to make your generator 1, 1, um, because 2 is even and 4 is also even, they share a prime factor of 2.
Yes.
Um, if you keep adding plus 1, 1, you will never reach uh, you will never reach 1, 2, for example.
One shoe. Oh, is that because when you say the generator being 1 1, that's going to be the generator of the product, which means that you need to keep adding those up, right?
Yeah, you're trying to see if the product is cyclic, right?
Yeah.
So, well, a natural generator to pick is just 1, 1 because that's the pair of the generators of the respective members of
Shoe,
the product.
G and H are cyclic in this case because of what again? Because modulo Z2 and modulo Z4 they generate.
Well, the generator is 1, right? You keep adding 1, you get all the elements.
Yes, that is true. But you're never going to be able to reach 1 2 in the product because you will always. Um, yeah, that needs to be what,
Because
1 3 instead?
Yeah, because if you do
Ah,
if you do like you
yeah,
start
that
with
is
zero
true.
zero, that's the identity, right? You add
Yeah,
1 1,
yeah,
and you do that again, you end up with 0 2.
yes. And then 1
But if
3.
you're yeah, but if you're trying to make this a cyclic group, you can't add anything else. You must keep adding 1 1, but because they share a prime factor, in this case 2.
No, no, but you can also add the generated elements from before, right?
I mean, you can, but they are just made up of the
Yeah,
generator
yeah,
you
yeah.
pick.
Yeah, that's not gonna help you. But just to clarify, you can in fact get the previous generated stuff and put in the mix. But isn't that like to make it maybe more convenient? But it's not gonna help you with the final answer anyway. Yeah, you're never gonna be able to generate one true with that, right?
No, you would need another element to generate the entire group, but then the resulting group is not cyclic because you have two generators instead of just one.
Fascinating. So essentially, the conclusion is, in order to make the products cyclic, you need the parts to be relatively prime.
Yes, basically.
Oh, cool. Um, yeah, that makes sense to me. I follow that. Even my monkey brain followed that. Okay. Any other comments, questions in E? Pretty cool. Pretty cool.
That conclusion is essentially what exercise 7 is asking about, just to note.
9 as well. Kinda, but that's kinda backwards.
Oh, it's talking about the orders of the how many elements, right? I wasn't thinking of that because in modulo those two things coincide, right? Cool. That's fine.
Oh, you can just just prove it from modulos and use the isomorphisms. So
No, of course you can, but that's not what 7 states. Um, okay, 9. Manin also said 9. So let cyclic A be a cyclic group of order Mn where they are relatively prime. Yeah, this is also that. Yeah, that's definitely that. Yeah, the syncing up process is very important, right, to these type of topics, which is unexpected, in my opinion. Okay, F. So kth roots of elements in cyclic group. Does anybody want to talk about F? And that's the last one for today. We still have 20 minutes, so do you guys want to talk about anything on F?
Do you have something to talk about, Steve?
Not really, no.
I spent some time on this, in particular, going like step by step on F1. Um, a lot of this just boils down to number theory, which is like not something I expected going into this book that we would go so heavily into number theory.
Yeah, that's what I said. It's very overwhelming that there's no note anywhere in the beginning saying, hey, you should also read at the same time this thing as supporting material.
Oh, to be fair, every concept of number theory we use is technically introduced in the book. So
Um, but that's
I
that's not really the same thing, Tevo, because it's one thing for the book to try to teach us number theory using algebra, because then we have to create the intuition on the spot. If you read the number theory stuff before or at the same time, a more dedicated material will try to create the intuition on you. Because, for example, I don't have any intuition about it. Marinho already did, already has since the beginning. So he's probably had an easier time when the book attempted to introduce those ideas than I had. See?
That's fair.
But yeah, I'm noticing as well a lot of um, relationships between particular properties of numbers, including or not being like GCD or prime, which I do know it's number theory stuff. Uh, but I guess as Stevo said, if you really think about it, you can in theory deduce those things by the algebra stuff. Even though, like I said, you have to come up with this intuition like on the spot. Anyway, you were saying about F1, Marin.
Yeah, F1 is actually kind of interesting because it you can actually go step by step, and it's intuitively not very hard because if A has order 10, then you can just say, okay, I'm going to use integers modulo 10, and then you can just do like normal decimal integer addition, and you just ignore any digits beyond the smallest one, and that just works. The thing is, like, yeah, I started going through F1, and then I was like, yeah, I'm not as obsessed with prime numbers as most mathematicians, so this is interesting, but not that interesting, to be honest.
Wait, but F1, you know the order of A, so you know that A, if you have 10 factors of A, you go to identity, right? Which is essentially can be isomorphically mapped to modulo 10, as you said yourself. But it's asking for what integers k does A have a kth root? So this is asking what are the k's that when to the power of another number is equal to A, right?
Yeah.
For what integers does A6 have factor root? Okay, so what are the k's that you found there?
Uh, well, I kind of lost my patience at some point, but like if you start from the bottom, zero. Well, clearly everything has a zero root because anything to the zero is just identity, right? So that's not interesting. Um, A to the first root, if you can call it that, is just identity, so that's also not interesting. The square root is interesting because you're basically saying, okay, is there any number where if I add it to itself, I get something else, right?
I get
And
something else. Hmm.
yeah, and then if you try to do that, okay, if you do I don't know, does one have a square root modulo 10 in the sense of addition, right? So the answer is actually not really, because if you try to do 5 plus 5, that's 0. If you try to do 6 plus 6, that's 2,
True.
not 1. But that does tell you that 2 has a square root, which is 6.
Yeah. I don't know if I'm following that. So what process? You said you did a process and you lost your patience. What was the process of that?
I just exhaustively checked each number at each k, basically.
When you say each number, do you mean like
From 0 to 9,
0
yeah.
to 9? Oh. So you exhaustively search from 0 to 9 if they ever generate what?
Okay, starting from k equals 0, is there
Yes.
any number from 0 to 9 where if I add two other numbers modulo 10, I get that?
Oh,
Basically.
I see. Mhm. Boring stuff. But okay. Um, okay. And then there is a k and an n, be any integers, and then the greatest common divisor of k and n. A linear combination of k and n is any expression ck plus dn, where c and d are integers. It is a simple factor number theory that an integer m is equal to a linear combination of k and n if and only if m is a multiple of their GCD. Cool. So that means that you can express m like this if m is a greatest common divisor between k and n. I didn't know that. Cool. From 2 to 6, Marinho or Tevo, do you guys have anything else to comment?
Not really.
Not really. Tevo, anything?
Not really, no.
Well, we still have 14 minutes to go. So next time we're going to talk about 12. I haven't read 12 myself. Um, I just want to confirm my understanding of F1 again, Marinho, because you said that you exhaustively checked that if you grab a number from 0 to 9 and you add two other numbers modulo 10, if you get to what?
Like, okay, so if you start with k2, because 0 and 1 are not interesting,
Yes.
is there any number in A, which is like integers modulo 10, where you can add two other numbers to get to it, right? And it turns out for k equals 2, basically you can get all of the even numbers, right? Because you can do 6 plus 6 equals 2, and 7 plus 7 equals 4, and then you can do
Yes,
like
yes.
8 plus 8 is 6, and
Yes.
then 9 plus 9 is 8.
Oh, okay. The k is how many times you're doing it, and the base is gonna be the number between the modulo 10. The b, right? Because it's b
Yeah,
to the power of k. K is the two that you said, so how many times you're doing the operation, how many factors you have, and the b is gonna be anything modulo 10. And then you have to exhaustively check. Yeah, that's boring, man. That's like.
yeah. So like 2 was easy, right? Because it's just the even numbers. And 3 is like, okay, you have to search for all the cube roots, but interestingly, 3 is relatively prime to 10, so actually pretty much every number has a cube root, right?
I have a question. In order for something to be a root, does it have to generate the entire modulo 10 stuff?
No, you're just saying, okay, I'm inside
Ah.
of modulo 10 land. I need a number for something to be a root to the k degree, right? Of another number. You
Yeah,
need to
so for 2 it's
you need
only
to
even
take
numbers.
you need to take the root and add it to itself k times, basically.
Uh-huh. And you were saying that everybody has a cubic root?
Because like if you do 3 plus 3 plus 3, that's 9. So 9 has a cube root, right? And then if
Yes.
you do um, well, 0 plus 0 plus 0 is obviously 0, so that's not interesting, but it's correct.
What about 2 though?
Um, well, to get to 2, you actually have to do, let's see, 2, 3. 4. Yeah, it's 4 because 4 plus 4 plus 4 is 12, which modulo 10 is equal to 2.
Yeah. Okay, so in this A, we always gonna have like cubic roots.
Yeah, for k equals 3, you always have a root no matter what element you pick because, well, the group has order 10 and 3 is relatively prime to it, so like it always works out
Ah,
that you get
that is a
something.
very interesting point, right? It's because 3 and 10 are relatively prime. Cool. Haven't thought of that. My
Yeah, and then
intuition
you
tells
just
me it must be the case, right? But now you know how to state what my intuition tells me. That's awesome.
yeah, and then when I got too far, I was like, yeah, this is slightly interesting, but not that interesting.
Yeah, I'd rather do something else with my time. Yeah, that makes sense. Yeah, no, and I got it. Really, I got it. So that's cool. And again, I apologize. I didn't put that much thought in the exercises, but I didn't have that much time to read either. So I read this, but and that's how I got to my questions. And I read the exercises, but I couldn't play much with it. Okay, so we're gonna finish earlier today, surprisingly. So is there anything else in this chapter that anybody else want to talk about? I don't think so, right? This is essentially like I don't know. It feels in the wrong place, doesn't it? Like we were talking about groups and we talked about some other stuff, and then eventually we are back into groups. This feels misplaced. This should have been earlier.
Maybe,
It,
maybe.
feel, it feels misplaced. Anyway, so if nobody wants to talk about anything else, next time we're gonna do chapter 12. And last comments before I finish the recording.
Modulo is awesome.
Well, yeah, again, right? So modulo is awesome once again. Uh,
But it has to be the proper Euclidean modulo, right? None of those truncating remainders that you see in
well,
C and the
to
like.
be fair, a lot of the stuff that we've seen so far would also um, remove the negatives, right? Because there's a very few exercises talking about negatives. Most of the exercises would also work with that.
Uh,
The problem
yeah,
with
but
Euclidean modulo is the negatives, right? That's when things get messy.
yeah, if you're not using the proper Euclidean modulo and you have negative numbers,
Then you're
all
fucked.
hell breaks loose. Yeah.
Yeah, everything is done. But again, most of the exercises we don't have to care about negatives at all. So they
Ah,
will work, which I think it's a plus in this case because that means that programmers have a chance. Have a chance. They will fail eventually because then we're gonna say, hey, there's all those numbers over there. You're not gonna be able to do anything about it. Uh, but I think that's a better. Like, I'm not saying we shouldn't have it in standard libraries, right? I'm not saying that. I think we should have both. Uh, but in this book, again, most of the exercises only deal with positive numbers. So that's you can actually like you should learn it definitely because it gives another understanding of modulo, which is the one that Marinho already explained, right? That in Python, if you use a negative index, the reason that works is because that's how it works in there. Uh, so that's cool. That's
yeah,
cool.
but there's actually a number theory reason that makes it legit, you know?
Oh, there is a number theory reason, and I'm also saying that's cool. Which again, this should be okay. We should make a remark that in Karuta standard library we should have Euclidean modulo.
Of course we should. Why would we not?
Well, because we have to implement it ourselves, right? And we are like so far we have two functions in standard library, which is equality and naturals.
Well, there are ways to implement it in terms of truncating and floor divisions. So even if the bean doesn't have it, we can just implement it ourselves. It's not hard.
Yeah, definitely. No, we should have it. We definitely should have it. Okay, I'm gonna finish the recording now.